On here, and we were looking at the example of sweating and shivering and body temperature as the variable and how that can be restored to set point through various negative feedback mechanisms. And the points that we want to reiterate here are that the change will always be in the opposite direction. So whatever the stimulus that was detected when we get back to set point, that requires a change in the opposite direction. And we've mentioned a few examples of blood glucose, blood pH, temperature, but there are so many other examples in the body, so many other examples of various homeostatic mechanisms and negative feedback mechanisms. Now, we also need to think about positive feedback, and positive feedback is a much rarer occurrence. The more common feedback mechanisms will be negative feedback. But very rarely, there needs to be a process that further stimulates a change. So the point of positive feedback is to amplify a change for a short intended period of time that can be stimulated by the effector organs. It can be a part of a bigger negative feedback loop. So an example is if we cut a blood vessel, let's say you have a paper cut on your finger and you begin to that clot begins to bleed. In order to correct that injury and to fix that clot, it's going to have a short time where more clotting factors are arriving to the site of the injury. So that requires more blood flow or more bleeding for a short time. And then the ultimate end to that cycle will be a negative feedback loop when that clot is formed and then the bleeding stops. So in order to think about positive feedback loops, think about them as being an intended amplification of a change for a short period of time that actually falls within a bigger negative feedback cycle. Another good example is the uterine contractions during childbirth. So those uterine contractions are regulated by a positive feedback loop. So they get stronger and stronger and stronger, which again is a change in the away from set point in terms of the state of the uterine smooth muscle. But that is intended and that is for a very necessary change for a short period of time. And then eventually those contractions will cease, and that will be the ultimate negative feedback change, which will end that cycle. So positive feedbacks are a small part of larger negative feedback cycles, and they are in order to bring us away from set point, but for a short period of time in order to bring about a desired result. So here's a third example of a positive feedback loop. So we have the pituitary gland, which secretes luteinizing hormone. Luteinizing hormone travels to the ovaries and encourages increased estrogen secretion. That increased estrogen secretion goes back up to the pituitary gland and encourages more luteinizing hormone to be secreted. So this doesn't happen for the entire menstrual cycle. This happens for a short window of time in order to encourage high levels of luteinizing hormone, which will then trigger ovulation. So in the days leading up to ovulation, this would otherwise normally be a negative feedback loop. So estrogen would actually turn off luteinizing hormone secretion. But in order to have the LH surge or that rapid increase in luteinizing hormone that is necessary for ovulation, there is a short window of time before ovulation where this is converted into a positive feedback loop, and high levels of estrogen actually further increase or amplify levels of luteinizing hormone. And then we have that spike in LH, and then we have ovulation, and then this goes back to being a negative feedback loop. All right. So positive feedback are a very rare occurrence, but are actually an important part of some larger negative feedback cycles. Now we can think about intrinsic and extrinsic regulation, ways that we can modify or modulate these feedback cycles and homeostasis in general. And this can occur through two processes in various organs. Intrinsically, this is going to happen within the cells and the tissues in the organ that is in question. So an example of this is the heart. And the heart has various mechanisms to intrinsically regulate its own rate and rhythm. We call this autorhythmicity. Extrinsic would be other external factors. This can be the other organs like the endocrine organs or the nervous system. And when we say endocrine organs, we mean glands. So maybe the pituitary gland or even the hypothalamus or the thyroid gland. So other organs outside of the heart can regulate the heart rate and rhythm as well. And then another component of extrinsic regulation is the nervous system. So neurons through the parasympathetic system or even through the sympathetic system, which is our fight and flight division of the nervous system, those neurons will innervate the heart and they can also modulate the rate and rhythm. So the various organs can regulate themselves internally, which is intrinsic, or externally, which is usually the brain and the endocrine system and nervous system.